In this video, I'd like to talk about some aspects of the quantum mechanical model of the atom covered in sections 7.5 through 7.9 in the textbook. We finished with the Bohr model of the atom, and we saw that while Bohr correctly calculated quantitatively the energy levels in the hydrogen atom to explain the line emission spectrum, we knew that the physical interpretation was incorrect. The electron cannot be circling the nucleus in an orbit like the moon around the Earth. And the big intellectual breakthrough came when scientists realized that when you're dealing with very, very small particles, we need to stop thinking about them as particles, but instead think of the electron in the atom as a standing wave, as a wave-like phenomenon rather than a particle-like phenomenon. And we've seen this before. We talked briefly in 7.2 about the dual nature of matter, wave-like and particle-like. Well, when you're thinking about the electron as being a wave, what that then means is that you cannot know both the position and the momentum of an electron to an unlimited degree of precision. There is a limit to how precisely you can know both of them. That is expressed in the Heisenberg uncertainty principle, which now everyone has heard of because of Breaking Bad. And it essentially says that the product of the uncertainty in the position, delta x, and the uncertainty in the momentum, delta mass times velocity, is greater than or equal to this constant, Planck's constant over 4 times pi. Okay? Now, Schrödinger then took it one step further and said, okay, if we're going to think of the electron as being a standing wave, let us derive some wave equations to describe the energy levels in the hydrogen atom, actual mathematical functions. Each wave equation we're going to call an atomic orbital, and it specifies the amplitude of the electron wave as a function of three-dimensional coordinates, as well as the energy of that orbital, and the wave functions are indicated with the Greek symbol psi, as a function of x, y, and z, the three-dimensional Cartesian coordinates. Well, for reasons we don't really need to be that concerned about, it turns out that the Cartesian coordinate system is not the best way to write these wave functions. Instead, we use spherical polar coordinates, which you may have run across in your math class at some point. It specifies the position of a particle around the origin of the axis system, not in terms of x, y, and z, but in terms of a distance and two angles. We don't need to go into it. All I want you to appreciate is that for these orbitals, these wave functions, we can actually write mathematical functions that look familiar. So for the three lowest energy orbitals, which are the 1s, 2s, and 2p, here are the wave functions. And you can see it incorporates things that you've seen before, exponential terms and trigonometric terms and whatnot. It's an actual mathematical function. Now, it turns out that the amplitude of the wave function doesn't have an actual physical meaning. It doesn't mean anything. To get something useful out of it, what we're going to do is to square the wave function, because when we square the wave function, that gives us what's called a probability distribution map. It is essentially either a diagram or a graph that shows regions around the nucleus where the electron in the hydrogen atom is most likely to be found. So that's also sometimes called an electron density map. And for the lowest energy state of the hydrogen atom, the ground state, which we call the 1s orbital, do you recall, we can look at both a probability distribution curve as well as a visualization. As you can see, the probability distribution curve shows that the likelihood of finding the electron in the hydrogen atom is maximum closest to the nucleus, but as you move further away from the nucleus, the probability decreases exponentially. And we can visualize that by using a series of pink dots to represent greater probability. The greater the density of pink dots, the more likely it is the electron will be in that location. And again, we see the electron is most likely to be found around the nucleus, and that as you move further away, the likelihood decreases. Now, you may recall that wave functions have associated with them quantum numbers, n, l, m, and s. We're going to skip that because quantum numbers are actually not part of the AP curriculum. But let's talk about what the orbitals look like and what their energies are. Okay. The Schrödinger equation gives basically the following: principal energy levels, which are sometimes called shells, sublevels within principal energy levels, which are sometimes called subshells, and individual orbitals within the sublevels, which are labeled s, p, d, and f. And I should point out that the principal energy levels in the quantum mechanical model of the atom are conceptually and quantitatively the same as the quantized energy level in the Bohr model. Bohr got the energies right. What he didn't get right was the physical interpretation, because he was thinking of the electron as being a particle rather than a wave. Now, I'll skip ahead to the result, Essentially, what we get from this is an energy level diagram for the hydrogen atom. Energy is increasing from bottom to top. Each row of horizontal lines represents a principal energy level. Even though we're not going to be using quantum numbers, we can say n equals 1, n equals 2, n equals 3, n equals 4 to indicate the first, second, third, and fourth quantized energy levels, which correspond to the ground state, the first excited state, the second excited state, and the third excited state. In the first principal energy level, we have a single sublevel, which is referred to as the 1s sublevel, that contains a single orbital. In the second principal energy level, we have two sublevels, which are called 2s and 2p. The 2s sublevel, like any s sublevel, consists of a single orbital, but the 2p sublevel, like any p sublevel, consists of three separate orbitals. In the third principal energy level, we have the 3s, 3p, and now the 3d sublevel, the d sublevel consisting of 5 separate orbitals, and the fourth principal energy level consisting of the 4s sublevel, the 4p, the 4d, and now the 4f sublevel, which consists of 7. Now, let's see what these orbitals look like. S orbitals are spherically symmetrical, and here are probability distribution maps of the 1s, 2s, and 3s orbitals. As you can see, as you go to higher principal energy levels, the orbitals get larger, which makes sense. You've got more shells of electrons, so the outermost electrons are going to be further from the nucleus. What you also see in the second and third principal energy level are nodes. A node is a plane or surface where the value of the wave function is 0, therefore the electron cannot exist there, which is kind of weird to think that the electron can be here or here, but it can't be in between. How does it get from one region to another? Well, you're thinking of it as a particle and not as a wave. Okay, waves have nodes. We often represent orbitals with a spherical diagram, not implying that the electron is always within that spherical volume, but suggesting that that represents what's called the 90% probability limit, meaning that 90% of the time the electron is within that particular volume. And these have been calculated for all orbitals. P orbitals are different. Here are visualizations of the 2p sub x, 2p sub y, and the 2p sub z orbitals, the three orbitals that make up the 2p sublevel. As you can see, each of these individual orbitals is oriented along one of the three Cartesian coordinate axes, x, y, or z. So for example, the 2px orbital on the far left shows one lobe of electron density pointing in the positive direction along the x-axis, and one lobe of electron density pointing along the negative x-axis. The yz plane, which is perpendicular to the z-axis, is a nodal plane. Once again, that is a plane where the value of the wave function is 0. The electron cannot be there. D orbitals are even more complicated. Here are 5 d orbitals. You don't really need to know this, but as you can see, as you go from s to p to d, you are increasing in complexity, you're increasing the number of lobes, and the number of nodal surfaces or planes. You want to see some f orbitals? Really? Here they are. Pretty awesome, huh? As you can see again, as you go to more populated sublevels with more orbitals, the orbitals get increasingly complicated. Let's move on to the next section, which is electron spin and the Pauli principle. It turns out that the electron, like most tiny particles, has what's called a magnetic moment, which has, in the case of the electron, 2 possible orientations in an external magnetic field. That property is called spin. Okay? And for the electron, there are 2 spin states, plus 1/2 and minus 1/2. If you want to think of it as like a top spinning on its axis, you can. That's not really what it is. It really is more a question of how it aligns its magnetic moment in an external magnetic field. Okay? Well, this led to the development of the Pauli exclusion principle, Wolfgang Pauli, who said that no 2 electrons in the same atomic orbital can have the same spin. If they did, they would be the same thing. If one electron in orbital has a spin of plus 1/2, the other must have a spin of minus 1/2, which leads to the following conclusion: a single orbital can hold up to 2 electrons as long as they have opposite spins. Now, up to now, we've only talked about the hydrogen atom, which only has a single electron, but we need eventually to move to polyelectronic atoms. And for that, the Pauli exclusion principle will be important. Okay. Now, it turns out that the Schrödinger equation, which gave us the wave functions that we call atomic orbitals, can only be solved exactly for the hydrogen atom. But the good news is that every other atom on the periodic table with 2 through however many electrons it has what are called hydrogen-like orbitals, which are similar in their shape and in their relative number. They just differ in energy and size. Okay? So hydrogen-like orbitals, they have different orbital energies and therefore different sizes. The problem is, once you have more than one electron in the atom, then the sublevels within a given principal energy level split in energy. And explaining that is a little bit complicated, but it has to do, and what we see is that the energy of the S sublevel is less than that of the P sublevel, which is less than that of the D sublevel, and which is less than that of the F sublevel. And that is sometimes explained by a concept that's called penetration. Here we see graphs that show the radial probability for the 3s, 3p, and 3d. And as you can see, based on this, the 3s sublevel can actually get a little bit closer to the nucleus. So the fact that it can get the electron a little bit closer to the nucleus than the 3p or 3d means that it's going to be lower in energy, and it will be filled with electrons earlier. So we can now develop our final conclusion, which is the energy level diagram for polyelectronic atoms. Once you have more than one electron in an atom, now this is the order in which the sublevels fill, and I will label them from lower energy to higher energy. 1s, 2s, 2p, 3s, 3p, 4s, 3d, and 4p. So you can see, again, the S is always lower than the P, which is always lower than the D, but curiously enough, the 4s orbital, again because of that radial penetration, gets filled before the 3d sublevel because it's actually lower in energy. Okay? This will be crucial. This diagram will be essential in the next unit when we talk about describing the electronic structure of polyelectronic atoms by writing what are called electron configurations and orbital notation diagrams. And you will recall the coolest thing in chemistry, why you don't have to memorize the order in which the sublevels fill. See you then.